Hello, here are some notes about density and pressure for fluids. We have gone over before that density has the symbol rho, and it's like a curly P. And the equation for density, we like to say, I love density, because you make a little heart and you cut it in half. Because the equation for density is mass in kilograms divided by capital V for volume in cubic meters. And so density is measured in kilograms per cubic meter. We talked a little bit about how the density of water is 1 gram per cubic centimeter. And if you have to convert that into kilograms per cubic meter, you would need to say that 1,000 grams is 1 kilogram, and that your 100 centimeters is a meter, but that doesn't cancel out all three of the cubic meters. It just only makes 1 instead of 3. So what we have to do is multiply by 100 centimeters, and now we've got square meters, but we don't want square meters, we want cubic meters, so we do 1 more times 100. And that's why in physics class, the density of water is equal to 1,000 kilograms per cubic meter. Talked a little bit too yesterday about how the density of the average person is about 985 kilograms per cubic meter, which means that they would float, because you're going to float when the density of the object is less than the density of the fluid. But we could even figure out what percentage of your body would be submerged by doing this new equation we have for specific gravity. Specific gravity can be found by taking the density of the object and dividing it by the density of the fluid you're trying to float it in. And so if we do that for a person, we would take the density of the object, which is the person, of 985, and divide it by the density of water, which is 1,000. And we would get 0.985, or 98.5%. This equation is actually going to tell us the percent of volume that would be submerged below the surface. So what that means is if you had a pool of water and you had a person in it, that when that person was laying down in the water, that 98.5% of their volume would be submerged. Just a tiny little bit would be floating at the surface because it's so close to the density of water. The other reason that they would give you the density of an object, besides to find the volume submerged, would be a funny way of trying to tell you the mass or the force of gravity of the object, right? Because density is equal to mass over volume, some problems would give you weird things like the density of a person, again, is 985, and maybe they'd give you the volume of the person, total, the total amount of volume that they displaced when they went under the water was something like 0.08. And so why would they give you that? It's so you could find the mass, that the mass would be equal to the density times the volume. I'm going to make these V's a little bigger. And so when we do that, we would get about 80 kilograms for the person, or we could then solve for the force of gravity if we needed to. So that's the important information that you really want to know about density. We're talking about maybe trying to do a lab where you tried to solve for the density of a penny. And so if you wanted to find the density of a penny, we were going to ask you to come up with hey, how would we find the mass of a penny? What lab skills would you use? Maybe we would want to use a digital scale here. And then how would you find the volume of a penny? And then we would say something like the volume of the penny is equal to the volume of water that it displaces. Stop it, Bella. Sorry, guys. So if you put the pennies in water and see how much water it displaces, the volume of the water it displaces is equal to the volume of the penny. You're fine, Bella. That's my dog. But we wouldn't just do a single mass, a single volume. We would want to be able to make a graph, right? The whole point would be, what could we graph so that the density of the penny could be our slope? And so we need to think about things like slope is found by taking change in y over change in x. And so if we want density to be our slope, the equation for density is that it's mass over volume. And so what that really means is that you would say that your y-axis would be your mass, and then your x-axis would be your volume. And so if you plotted all of your different masses in kilograms and your different volumes in cubic meters, that's a good way of getting rid of some of the error, where you would just draw this best fit line, and the slope of this best fit line would be equal to your density of the penny. Okay. The other topic we introduced yesterday was the idea of pressure. And so the idea of pressure is that pressure is related to force. More force causes more pressure. But pressure is not just the force, it's the force that is exerted per area. So even if you have a very large force, like the whole weight of your body, if you extend that over a big, huge surface area, it's going to reduce the pressure on that area. Now, force is measured in newtons, and area is measured in meters squared. So pressure should be a Newton per meter squared, and you could say that it is, but really we named it after somebody, right? So it's called a Pascal. Pressure is measured in pascals. We are under a lot of pressure right now. We're under what's called air pressure. When we talk about air pressure, we would say that the pressure that air exerts is equal to 1 atmosphere. Bella, fine ice, you need to stop. Enough. That 1 atmosphere is equal to air pressure. It's atmospheric air pressure. So what you could do, though, is that's not right in the right units. We're not going to know how many newtons that would be per each meter squared that it's applied to. The conversion is 1 atmosphere is equal to 1 times 10 to the 5th pascals. So like 100,000 pascals would be 1 ATM, 1 atmosphere. And so you would think that we would be crushed under that huge amount of force for the surface area of our body. And the answer is we kind of are, that the air pressure keeps us like the shape and size we are because it pushes down on us, but it also pushes up on us. And it pushes us to the left, and it also pushes us to the right. That pressure gets exerted equally in all directions onto a surface area. And so we're not just getting pushed down, but any surface that's exposed is also getting pushed up. And so we don't really feel the effects of that air pressure when we're getting it from all sides. What we like to do is put a person into a garbage bag. And then inside that garbage bag, what we would then do is we would suck out all the air from the inside. So if you remove all the air from the inside, what happens is you can feel the pressure from the outside pushing on that garbage bag, but there's no air on the inside to push back. And so basically you feel trapped. You're like shrunk wrap inside the garbage bag and you can't get out because you feel that big amount of force pushing on you from the outsides. And normally there's force from every direction, and so it's kind of balancing out. But if you suck the air out of the inside and there's only air on the outside, you're going to feel that big force over your body from that air pressure. Another example of this that we like to do in class is to have like a meter stick. Really, it's a yardstick because they're thinner. And so we put the yardstick on the lab table. And if you hit the yardstick while it's on the lab table, it's just going to go flying. But if you take newspaper and you put that newspaper down so that it covers up that whole yardstick and it has a very big surface area, and you can get all the air out from the underneath of it. Basically, the more surface area you cover when take the air out of it, the more force you can get acting down on top of that meter stick. And the reason you would do that is then if somebody goes to hit the meter stick, just with your hand, like a karate chop, that when you hit the meter stick, you can actually break the meter stick because the newspaper is getting such a big force from all of the air pressure pushing down that it keeps the yardstick still. And so when you hit down on it, this part is going to just break right off because the rest of it is able to stay still. And so those are examples of how pressure exerts force in all directions. But if you can remove some of the fluid that's causing the pressure, you can remove some of that force that it causes. Because pressure can be caused by different fluids. And so you kind of wonder, like, how is that pressure caused by a fluid? Great question. Maybe we have like a beaker of water. And we know that that water is pushing on all sides of the container, but that it's especially pushing down on this bottom surface down here. And so if we wanted to know how much pressure there was on that bottom part, we could use the equation pressure equals force over area. And the force would be equal to the weight of the water. So this is going to be equal to the force of gravity of the water inside the beaker. And the area is going to be the cross-sectional area right here of the bottom of the beaker. And so that force of gravity of the water over the area is causing the pressure at the bottom. To solve for force of gravity, we could say that the force of gravity of the water is equal to the mass of the water times g. But we don't always deal with mass of water. Oftentimes we like to deal with density. And so instead of the mass of the water, we could say something like, well, we know that the density of the water is equal to the mass of the water over the volume of the water that's inside of here. So the total volume inside of here. So as we're starting to try to put some of this together, we're going to say that the pressure is equal to, we can start with the mass of the water times g over that surface area of the bottom surface. But we could replace that mass of the water. We could replace that mass of the water with the mass of the water is equal to the density times the volume. So the pressure is equal to the density of the water times the volume inside that container times g all over the cross-sectional area of the bottle. And you could leave it that way. But there's a relationship between the volume and the area. The idea is that the volume is equal to the area times the height. So this right here is the height. The volume is all the water inside, and the area is the surface area of the bottom, that cross-sectional area of the bottom. So as you do that, if you replace volume with area times height, what we have done is derived the equation for pressure due to depth below the surface of a fluid. And so what we get here is just a workable equation that it's the density of the fluid times, we're replacing V right here with, let's do density equals, let's do this equals density area times height G over area. There we go. So it's the density of the fluid times G times the height. And the height is really the depth of the fluid. So the deeper you go, the more pressure you feel, which is why when you go deep sea diving or whatever, the pressure gets so high on you and your ears pop and all that. When you change your depth, it changes the pressure that you feel due to the fluid you're in. So we would say that the pressure exerted on that bottom area of the cup is due to the density of the water, gravity, and the depth of the water. The deeper the water is, the higher the pressure would be. And so we could use that equation to try to explain why air pressure even exists, right? Like why is there air pressure? Well, if here is the earth and here is us, not to scale, and here is the end of the atmosphere, we would be able to say, all right, at what depth are we underneath the fluid of air, right? So we are feeling this air pressure of 1 atmosphere. And the pressure of 1 atmosphere, or 1 times 10 to the 5th pascals, is due to the depth of the air that we're under and due to the density of air, which is about 1.3 kilogram per cubic meter. So as you work this out, you could solve for, like, what is the depth we are beneath the air if the density of the air is staying constant all the way out to the edge. And so if we use this equation, that pressure equals the density of the fluid times G times that depth that we're under, we could say that 1 atmosphere of air, 1 times 10 to the 5th pascals, is equal to the density of the fluid, which is air, times G, which is 9.8 or 10, times that depth that we are underneath the air. And so if we calculate that out, 1 times 10 to the 5th divided by 13 is a height of 7,692 meters below the surface of the air, causing that amount of air pressure to be pushing on us. Now, when we look at the pressure that we're under because of air, the answer is always just 1 times 10 to the 5th pascals. You don't have to keep calculating it. We already knew that answer was the pressure. But that pressure existed up here on the water as well. So up here we had air pressure because we were open to air, and we had the added pressure due to the depth of the fluid. And so that's why they talk about sometimes the difference between gauge pressure and absolute pressure. If they're talking about just the gauge pressure, they're talking about just the pressure due to the new fluid besides the air times G times that depth. But when they're talking about absolute pressure, that means the total pressure you're under, which is basically just going to be your gauge pressure plus your atmospheric pressure. And so a way to sub that in would be to say that your absolute pressure that you feel is going to be equal to rho GH plus 1 times 10 to the 5th pascals. And so depending on if they want to know what added fluid you're on, what added pressure you have because you're below the surface of a fluid, or the total pressure you have because of air and the fluid. That's how you would interpret, like, when to use which version of that equation. All right, hope you enjoyed